Alrighty. Morning, everybody. Welcome back to Calc 3. Plan for today is we're going to start by finishing off our discussion of lines, and then spend kind of most of class today focusing on planes. Sort of how do we find equations for, / how do we look at trying to just kind of visualize these kind of two-dimensional flat surfaces within R3. Got office hours this afternoon at 2 o'clock, tomorrow morning at 10, and tomorrow afternoon at 1 o'clock. And as far as homework goes, I've posted some practice problems for Standard 4 on Blackboard. Encourage you to give those a look. Just so you know, the Standard 4 quiz is not going to be until next Monday. I'm planning on, we're going to spend the rest of class today and probably about half of class on Friday still kind of working our way through the rest of Standard 4. Graded your Standard 3 quizzes, as well as a few other quizzes you'll retest it on. So I'm going to go ahead and pass these back. So, Katie. Him. Avery. Lindsay. Awesome. Sarah. Hannah. Sorry. I feel like I've got like 2/3 of the names down. Still working on this. Sean. Jerry. Luke. Dog. Wait. John. Put some acrobatics in here. Emily. Jack Boy. Bennu. Olivia. Will. Lori. Jacob. Jack Smith. Jackson. Holly. Rihanna. And Matt. Anybody have any questions or comments before we get started for today? What type of math is commonly discussed between seabirds? The type of math that's often discussed between seabirds is intergoal calculus. Okay, so last class we introduced and talked about how to find lines in 3 or higher dimensions using this sort of idea of parametric coordinates. And what we said was if you have a line in R3 that happens to pass through the point P0, given by B1, B2, B3, and that is parallel to the vector A equals A1, A2, A3, so in other words, A here was our slope vector, then you can write out that formula for that line as being R of t equals AT plus B, where B, this corresponds to a point on your line, A was given by the slope vector, and if you write that out in sort of separate equations for x, y, and z, we get x of t is a1t plus b1, y of t is a2t plus b2, z of t is a3t plus b3. And before we move on from talking about lines, there is one more question I wanted to ask the class regarding lines, and that's this one. So I'm at the bottom of the second page of the packet here. Find an equation for the line that's going to be passing through 2 points let's say P naught equals 1, 2, 3, 4, and P1 equals 0, -5, 8, -10 in R4. So this one's a little bit different than the problems we were looking at towards the end of class on Monday. Because in those problems, we were explicitly given a slope vector and said, hey, here's a point on our line, here's a vector corresponding to slope, let's find an equation for the line. This one's a little bit trickier though, because we're not given a point and a slope vector. Instead, we're just being given a line and being told 2 points on the line. So we're being given a P naught and another point, P1, and being told find the line which passes through these 2 points in R4. So what do you think our approach could be here? Something we could try that would allow us to somehow use this AT plus B equation for a line. Tyler?
Maybe you could find the displacement vector and then use one of the points as like the B vector.
Okay, we could just use one of these 2 points as the B vector. Sure, that could be either point, just need any point on the line. And you said find displacement vector. Displacement from what to what? Okay, so you want to find the displacement vector from P naught to P1. And what would that do for us?
That would give you like the direction that the line is in.
So it sounds like you're proposing we use this displacement vector, P naught P1, as our slope vector?
Yeah.
I like it. Let's see what happens. So if we want our displacement vector from P naught to P1, that means we need to take our vector for P1 minus our vector for P naught. Which if we do that, we'll get 0 minus 1 is -1. -5 minus 2, which is -7. 8 minus 3, which is 5. And -10 minus 4, which is going to give us a -14. And so this P naught P1 displacement vector is going to then give us a vector which, if we started at P naught, would take us to P1. We're going to shade it in here. And since that's a vector that happens to correspond to sort of the direction that our line is pointing, it's telling us if you start on this line and if you travel along this vector, you'll still keep being on this line. I agree. I think this works very well as our as a slope vector that we could use. So if we were to use the slope vector, we get R of t is equal to -1, -7, 5, -14 t plus some point on our line. Does it matter which point we pick to be sort of our base point, like our B vector here? Why not?
Well, if it's the same direction, it's gonna hit the other one anyway. Like if you start at the point and go with the slope, following the slope of the displacement vector, you're gonna run into either one if you extended it.
Yeah, I agree. If we start at P naught and follow our slope vector, that would take us to P1. But wouldn't it be the case if we started at P1 that if we took this slope vector, it would take us away from the other point?
Well, like if it's not a directional vector anymore, and it's a line going in both ways.
The line is, yes, but
Yeah.
the vector still is pointing in just one direction.
Okay, I just thought it was like you're doing a line, not just like the parametric equations for a line, right? Not for a vector.
This is true.
So doesn't it just hit both?
It's a little bit interesting, because technically our slope vector is something pointing in one direction, even though you're right that the line itself is going to be heading off in both directions. And I think this sort of gets to the idea that it doesn't matter if our slope vector is the exact slope vector, or if we were to take a scalar multiple of it and make it point in the opposite direction, it would still define the same line for us. So ultimately, I think you're right, it doesn't matter which point we pick. Mainly corresponding to the fact that if we were to start at P0 and travel in the direction of our slope vector, that's going to keep us on our line, take us to P1. If we were to start at P1 and then take our slope vector, I don't have enough room to fully draw it out, but pretend I do. It's not going to take us to P0, but it will still keep giving us points that are on our line. It's still going to follow the same direction that the line does up this way. And so I would agree, we could pick either our P0 or our P1 here to sort of be the kind of the point that we're plugging in for our constant value vector. So I'm going to use P0. 1, 2, 3, 4. And there we go. There is our formula, our parametric formula for the line. Or if you prefer, you could write it out using 4 coordinates and say something like x of t is negative t plus 1, y of t is equal to negative 7t plus 2, z of t, what would we have as our sort of our third parametric equation here? Alan? 5t plus 3. I agree. And then our last coordinate, let's call it w, is going to be negative 14t plus 4. So we get a nice set of parametric equations like this, where kind of all these constant values at the end just correspond to a point on the line. And all of these scalar values that we're multiplying t by, this vector right here is going to be giving us our slope vector when we kind of write out each of these coordinates individually. So, just like you would in like a Calc 1 setting, if you want to find a formula for a line and you're given 2 points, just use the 2 points to find the slope. In this case, the slope vector we could use would work, something that would work well is just displacement vector from P0 to P1. Or from P1 to P0 if you prefer. That would point in the exact opposite direction, but would still define the same line for us. Any questions, comments, or concerns? Okay, and that's all then I have to say about lines for now. Now I want to transition to talking about planes. So, without looking at the next page and telling me exactly what formula we're going to use, if I were to say I'm thinking of a mathematical plane, what sort of shape does that make you think of? Or to say like a plane in R3. What kind of shape are you sort of visualize when you think about that? Excellent.
A square that goes infinitely
A square that goes in.
in 4 directions.
Say that again?
A square that goes infinitely in 4 directions.
A square that goes infinitely in 4 directions. Sort of like if you were to take this blackboard, for instance, and make it keep going to the left forever, to the right forever, up forever, and down forever, something like that. Yeah, I would say so. Or if we were to take our chalk, if I were to use my Hulk strength, rip the chalkboard off of the wall, and rotate it, that would also look like a plane, assuming it extended forever in the 4 directions. A plane in general, at least intuitively, is you're thinking of something that looks like a copy of R2. It's like a flat plane, but it might not be in two. But it might have to exist in 3-dimensional space or 4-dimensional space or something. And so the way we're actually going to define a plane, though, is going to be using this idea from Standard 2 of orthogonality. So let's write this down and see what happens. I wish I could rip this chalkboard off the wall. I would move it to a different wall so that the screen doesn't block half of it. All right. So here's the idea of what we're going to be doing. We're going to let P naught be a fixed point in R3. And N is going to be a displacement vector starting at P naught. So in other words, let's say we're gonna when we're defining a plane, we're always gonna want to start with some base point, call it P naught, and N is going to be a vector that's sticking out of P naught. N, by the way, is going to stand for the normal vector. How we're going to define a plane, ultimately, is that a plane is going to be a 2-dimensional surface. It's going to look something like this. Whenever I draw a plane on the board, I'm going to draw it as a rectangle, but I want you to think of that rectangle as extending out forever in, say, this direction and that direction, kind of going diagonally into the board and out of the board. Like an entire 2-dimensional surface that goes on forever, but I can't really draw that because I don't have an infinite amount of time or an infinite piece of chalk to work with. A plane is going to be a set of points, P, where if you were to take the displacement vector from P naught to P, it would form a right angle with N, our normal vector. So if we pick this point P1, P naught, if P1 is in the plane, then the displacement vector from P naught to P1 is going to be perpendicular to our displacement vector from P naught to N. If we had another point in our plane, let's say this is P2, then the displacement vector from P naught to P2 should also be perpendicular to our normal vector N. If I had another point, let's say P3, that happens to lie in our plane, then the displacement vector from P naught to P3 should be orthogonal to our normal vector N. Our plane is just always going to be made up of all these points whose displacement vectors from P naught are perpendicular / orthogonal to the vector N. So let's write that down. So the plane, and oftentimes the typical letter you use to refer to a plane is actually the Greek letter pi, a capital pi, unlike the lowercase pi, which is 3.14 blah blah blah. By the way, if you want to be a true mathematician, you have to memorize some amount of digits of pi. I can get up to 3.14159265357, and that's all I know. That's kind of embarrassing. I know other mathematicians who know hundreds of digits of pi. You don't actually have to do that. Anyways, the plane pi is the set of all points P in R3 that's going to satisfying that the displacement vector from P naught to P is orthogonal to N. So in other words, it's the set of all points P that's going to satisfy the equation that if you were to take the normal vector and dot it with the displacement vector from P naught to P, that is going to give us 0. Because if you recall, we said back in standard 2, the way you can check if two vectors are perpendicular or orthogonal to each other is if their dot product comes out to 0. So if your normal vector dotted with the displacement vector from P naught to P comes out to 0, then the point P is in your plane. If the dot product is not 0, then forget about it. Your point lies outside of the plane that we're going to be looking at. So what does this look like, Dr. Nursel? What kind of equations or formulas does this actually lead us to? Well, typically, you end up doing something like this, where P naught and N are going to be constant vectors. And you often end up seeing something like if P naught is equal to some constant vector x naught, y naught, z naught, and if the normal vector you'll often refer to as a capital A, capital B, capital C, so these are all constant values, and if P is a vector that's made up of variables, x, y, z, if you were to substitute kind of these three vectors into this equation, what you would end up with is that 0 is equal to the normal vector, a, b, c, dotted with the displacement vector from P naught to P. Can anybody tell me the first, what would the coordinates of our displacement vector, P naught P, look like here? If P naught is x naught, y naught, z naught, and P is x, y, z? Elliot?
Would it be x naught x, y naught y, z naught z?
Close. I don't think we're going to be multiplying them together, because finding displacement vector from one point to another typically doesn't involve multiplying the coordinates. What do we have to do instead?
X minus X naught,
Yeah, I think we need to subtract, because the general formula for how you find a displacement vector between 2 points is you just take the coordinates of the second point minus the coordinates of the first point. So first coordinate of P minus first coordinate of P naught would give us an x minus x naught, and then ditto for the other coordinates. Which, if we ended up taking our dot product here, would give us the expression 0 is equal to a times x minus x naught plus b times y minus y naught plus c times z minus z naught. And this right here is actually what's going to be called the standard form of a plane. Is by writing it out like this, where you just have an equation of the form some constant times x minus x naught plus some other constant b times y minus y naught plus another constant c times z minus z naught is equal to 0. There's actually a second sort of equivalent way of writing out the standard form of a plane, and that's by saying, doing this, where we can say, where if we let d be equal to the expression a times x naught plus b times y naught plus c times z naught, we could also rewrite this in the following way. You could write it as 0 is equal to ax minus ax naught plus by minus by naught plus cz minus c times z naught. For here, I just expanded this out, distributed A, B, and C. I'm going to combine all the terms with x, y, and z to get ax plus by plus cz minus the expression ax naught plus by naught plus cz naught, which is the same as saying ax plus by plus cz minus this d expression. And what we get if we add d to both sides is going to be the equation ax plus by plus cz is equal to d. And this right here is going to be a second way that we can actually write out what is the standard form of a plane. So if I were to ever ask you on an exam or a quiz question, give me the standard form of the plane that does loop. You could either write out this form, write it out in this form, or you could write it out in this form, where you just have ax plus by plus cz equals some constant, where the constant d is just going to be this product up here. So before we actually go in and look at a specific example, I want to see what questions you all had about kind of what we've seen so far. How a plane is defined, where do any of these equations come from? Any questions before we start plugging in some numbers and look at a specific plane? Yeah. Huh?
So, the way we define does that mean that the ax plus cz is equal to ax naught plus by naught?
Sure. You could just take this d and replace it with this expression. And I like writing it out this way because it's kind of a nicer, more compact equation. But you could certainly replace that d with all of this stuff.
And is that just because x is orthogonal to p naught above?
You can't really say that n is orthogonal to p or to p naught. Let's squeeze this up a little. Let's say this is our point p here. You can't really say that n is orthogonal to p or to p naught individually. Because n can only be orthogonal to other vectors. So all of that comes from the fact that n is orthogonal to the vector going from p naught to p. Which, if you kind of go back to our original equation here, is what gave us this equation right here. And then when I started substituting in, we said we let n be equal to abc, p naught p then had to be all of this stuff. Using the fact that n and the displacement vector p naught p were orthogonal is ultimately what gave us this equation. Good question. Let's look at a specific example where we're actually looking at a few different points and vectors and see what sense we can make of it. So I'm going to be looking at the next page of the packet, and our goal is going to be to do this. Our goal is going to be to find an equation for the plane that's going to pass through the point P naught equals 1, 5, 3 with normal vector n given by 3i minus 2j plus k, or if you prefer, by 3, negative 2, 1. So we want a plane that happens to pass through this point and that's going to have this normal vector. So before we start trying to compute any of that, let's actually just see if we can visualize what does this plane look like. Oh, come on. Hate how this thing turns off if you don't do anything with it for a minute. So I'm going to go to CalcPlot 3D and just see if we can figure out what this looks like. what's this? Where's my cursor? Oh, there it is. So if I go into browser, and go to Calcplot 3D, which again is linked to on Blackboard if you want. Pretty, go away. Let's see what happens if we first of all look at our point and our normal vector. So I'm going to plot the point, 153. 153. I'm going to make it blue because I like the color blue. Where is it? Oh, there it is. It's way out there. So I'm going to go in here to click this button, which will allow me to zoom out, so to speak. And here's our base point, P naught, that I just graphed. If we graph our normal vector coming out of P naught, we're going to get this vector. Let's see, 3, -2, 1. And we want it to be a displacement vector that starts at the point 153. And I'm going to make this vector red with a width of 4. So here's where we're at. We have a point right here, P naught, and a normal vector n sticking out of that point. So the plane, which we would ultimately like to find a formula for, I'm going to put in the answer here, look away for a second. It's going to look like this. It's this flat two-dimensional surface. We orient the axes properly. Let's see if Z6 straight up. It's going to look something like this, where any point on this surface, if you were to take the displacement vector from P naught to any point on the surface, say here, that displacement vector is going to be orthogonal to our normal vector. So in other words, our normal vector is going to stick out of this plane at a right angle. And what we should be able to do is, just being given a base point, P naught on our plane, and this normal vector n, we should be able to find a formula for our plane using kind of what we just talked about with ax plus by plus cz type stuff. So any questions about kind of the visualization here before we move on to actually doing some computation? All right. And mute the screen for just a second. Let's see what happens if we do this process. So if P equals XYZ is a point on the plane, according to our original definition of a plane, we should have that 0 is equal to the normal vector dotted with the vector that starts at P naught equals 153 and points to P. So n dot displacement vector should give us 0, which if we plug in, our normal vector was 3, -2, 1. If our point P is XYZ and our point P naught is 153, what's the displacement vector from P naught to P going to be? Here's I'm not blocking anything. What would be the vector that would take us from the point 153 and end at the point XYZ in the plane? Emily?
X minus 1, y minus 5,
Yeah, just the point coordinates for P, X, Y, and Z, minus the individual coordinates of P naught. So that'll give us an X minus 1, or, sorry, X minus 3, Y minus, No, it was x minus 1. Sorry, I'm mixing up which vector is which. X minus 1, y minus 5, z minus 3. X, y, z minus the coordinates of our starting point. Which if we take the dot product of, we're going to get 0 is equal to 3 times x minus 1 minus 2 times y minus 5 plus 1 times z minus 3. And this would be one way that we could write out our standard form for the plane. So 0 equals 3x minus 1 minus 2 times y minus 5 plus z minus 3. Or, if we wanted the other way, the ax plus by plus cz equals d form, we could just simplify, multiply this out, take our constant term that we end up with, and move it over to the other side, which would give us 0 is equal to 3x minus 3 minus 2y plus 10 plus z minus 3, which is the same as taking 3x minus 2y plus z minus 3 plus 10 is plus 7, minus 3 is plus 4, and ultimately we could end up with the formula right up here so you all can see. (3x minus 2y plus z is equal to negative 4. Where the negative 4 just came from subtracting 4 from both sides of this equation. Which, lo and behold, is exactly the formula that I came up with that gave us this graph. Where 3x minus 2y plus z equals negative 4. Any point x, y, z that satisfies that equation. So, for instance, some points we could plug in would be like 0, 0, negative 4, or 1, 1, 1, or let's say 1, 2, 3 minus 4 is negative 1, minus 3. Any point x, y, z satisfying that equation is going to pop up somewhere in this point. If we were to graph that point, it would be on this flat two-dimensional surface. Whereas any point that didn't satisfy that equation would be somewhere off of the plane in R3. Questions or comments, either about the picture of what's going on here or the kind of the computation that's currently hiding behind the picture? In that case, I have a problem that I'd like for you all to try out, which is the second problem, this keyboard, the second problem in this packet, which is on this page, which is this one, where this time, instead of giving you a point and a normal vector, we're going to look at what happens if you have a plane that passes through the point 2, 0, 5, Get extra big so you can see it. So if this is our base point, and let's say we have two vectors, both of which are going to stick out of this base point, where our first vector is 2, 4, 1, sticking out of 2, 0, 5, which I'll make this vector, I don't know, purple. Doesn't do that. Let's make it 3. And if we have a second vector that sticks out of that same point, negative 1, 0, 2, (2, 0, 5), and make this one a dark green. Here's my challenge. I want you to find a plane that contains this point and that contains both of these two vectors. So in other words, let me get a good angle on this. I want a plane that if we were to graph out the plane would look something like this. Where the point and both vectors starting at that point happen to lie inside of the plane. So writing this out on the board, the question will be to find an equation for the plane that passes through the point P naught equal to 2, 0, 5 that is parallel to the position vectors V equals 2, 4, 1 and W equals -1, 0, 2. And when we say that the plane, by the way, is parallel to the position vectors V and W, that's the same as saying if V and W were treated as a displacement vector starting at P naught, that those vectors would lie inside of the plane. Let's go ahead and take a couple minutes, talk to your neighbors, and see if you can find a way to find an equation for this plane. And my hint to you is you're going to first need to find the normal vector in a way where that normal vector, let's say if this is our P naught, if this is V inside of the plane, W's inside of the plane, you're going to need your normal vector N to be perpendicular to both V and W. Let's go ahead and take a couple minutes, see if you can find a way to do this. If you feel like you need help getting started or you're just kind of not sure what to do, how you would find your N, feel free to flag me down or to ask someone sitting nearby. Yes, I know I'm giving you, if you look at the screen, you can find the plane and the normal vector. See if you can find it without looking at the screen. you feel like you have a solution, that you kind of understand what's going on, I encourage you to turn to someone sitting nearby. Dr. Gerstle can speak words, and see if they agree with what you have. And if neither of you feel like you know what you're doing, feel free to flag me down, and I can share my thoughts. So let's take a couple minutes now and kind of come back and share our thoughts as a class, because I saw a lot of you kind of have a nice, ingenious way of coming up with a normal vector here that's going to be perpendicular to v and w if we shift them all to start at our p naught. Anybody like to share the approach they took for how to find a normal vector? Yeah. Jay?
I took the cross product of v and w and used that as the normal vector, and then took the dot product of the normal vector and the displacement vector from P0, which is T05, then I just have P as x, y, z. And then I solved the equation out.
Okay, cool. So let's go back to kind of the first half of what you were saying. So it sounded like to find something orthogonal to v and w, you took the cross product of the two, which I think works great. Because as we saw in standard 3, one nice property of the cross product of two vectors in R3 is that it will always give you something orthogonal to the original two. So if we do that, we'll get, what was our v? 241 cross -1, 0, 2, which we write that out. in determinant form, we'll get the determinant of the matrix with first row ijk, second row 2, 4, 1, third row -1, 0, 2, which will give us I times the determinant of what you get if you remove top row and left column, which is 4, 1, 0, 2, minus j times the determinant of 2, 1, -1, 2, plus k times the determinant of 2, 4, -1, 0. We remove column and row with k in it, which for I is going to give us 8 minus 0 is 8i, minus 4 minus -1 is positive 5, so minus a 5j. 0 minus -4 is a positive 4k, which will give us 8, -5, positive 4.
So when I did this, I did the cross product of the displacement vectors from V and W from the point they were given.
Ah, okay. So,
It very well could be. I wouldn't be surprised.
don't sound so unconfident. So you took the displacement vector from P naught to this point here. How did you find what this point was?
It was 2, 4, 1 minus 2, 0, 1.
Ah, okay. So you actually found. So here, V I had as a vector, kind of telling you which. I guess the way I thought of this was V and W already were displacement vectors. They're telling you if you were to start at P naught and travel in the direction V is pointing, where do you want to still stay in the plane, and if you travel in the direction W is pointing, starting at P naught, that's where you -1, 0, 2, you still stay in the plane. So when you typically see this type of problem, V and W already are your displacement vectors. I know I wrote it in kind of an awkward way because this is how the book writes it, as find the plane that is parallel to the position vectors V and W. What that means is if the origin is, say, down here, and we wrote out V and W as position vectors like this, basically saying the plane is parallel to these position vectors is the same as saying if we were to shift these position vectors and move them up to be displacement vectors pointing in the same direction at P naught, they would still be in the plane. I think, though, if I had given you something a little bit different, if I had given you coordinates for the points right here and here, and then said, find the plane, then you would have to calculate new displacement vectors from P naught to here and P naught to there.
So do we just conclude, like, how would we have known that we were displacement?
You just kind of have to try and visualize what the problem is telling you about them. Is if they're parallel to the position vectors 2, 4, 1 and -1, 0, 2, that just means the plane is pointing in the same direction as these vectors are going, so that if you were to treat them instead as displacement vectors, they would lie inside the plane. If you see a question like this again, this notion of being parallel to these position vectors really just means the same thing as containing the displacement vectors. A little bit confusing notation, but that's typically what the book means. I don't know. I try to make things kind of match with the book, but sometimes the book does things a little bit confusing. Any other questions about how we found the normal vector?
I guess what happened if you cross, if you did W cross?
Yeah, zoos. I'm actually planning on talking about that after we finish the process. So, can you hold on to that thought for just a second? It's a good question. So let's actually finish finding the plane here, and then we'll do a comparison of what if we did a switcheroo. Yeah, Tim?
Why isn't it -4?
Because you take top left times bottom right minus bottom left times top right. So you would end up with something like 0 minus a -4 for multiplying, which comes out to a positive. So let's see what we get when we use this plane for. So now we have a normal vector that we can plug in. So Jerry, earlier I think you said you just picked your P naught, and then for your displacement vector P naught P, you just used one of V and W. I might be misremembering, so don't let me put words in your mouth.
No, the displacement vector I used the point P naught, and then P was just X, Y, and Z.
Gotcha. So you just use the P naught P. Okay. So if we do that, we'll get 0 is equal to normal vector dotted with P naught P, where we're assuming here P is a point in a plane. And if we write that out, that'll give us that 8, negative 5, 4, dotted with the vector P naught is 2, 0, 5, P is x, y, z. This is going to give us x minus 2, y minus 0, so just y, z minus 5, that this dot product should come out to 0. This anymore, which will give us 0 is equal to 8 times x minus 2 minus 5y plus 4 times z minus 5 is 0. Which if you wanted to, you could stop here. That's perfectly fine. Or if we multiply out and keep going, we'll get 0 is equal to 8x minus 16 minus 5y plus 4z minus 20, which is the same as 8x minus 5y plus 4z minus 36. And then we end up with 8x minus 5y plus 4z is a positive 36. So any point satisfying this equation is going to be a point on our plane. Ellen?
Is there some kind of geometrical representation of that constant of it? Like do anything in the
Yeah, so that constant, if you recall, was our d, which was that ax naught plus by naught plus c times z naught is kind of where that 36 actually is coming from, which is actually the same as taking the dot product of ABC with x naught, y naught, z naught. So that constant is actually coming from taking the dot product of the normal vector n with your sort of your P naught point, if you were to treat that as a vector instead. And it doesn't really tell us too much geometrically looking at the graph necessarily. Because P naught you're typically thinking of in this example as being a point, not as of an arrow, a vector that's pointing in some direction, just a fixed point in space. But if you were to treat P naught as a vector, as instead of just being a point, then this dot product is what that constant term at the end would come out to. What is kind of going to have a lot more geometric significance, though, is if you peel off these scalars on x, y, and z, that's going to be the coordinates of the normal vector 8, negative 5, 4, which is, if you recall, that vector that's sticking out of the plane at a right angle to the plane. So Avery, I think you mentioned earlier, what would happen if we had taken W cross V instead of V cross W here? Well, the cross product is and I think that's a good question, so let's explore what would happen if we did that. I'm going to go ahead and erase this. I think we're done with that for now. One thing I will say is that if we had taken W cross V, remember the cross product is anti-commutative, so that would have been the negative of V cross W. So we would have gotten negative 8, positive 5, negative 4, instead of positive 8, negative 5, positive 4. And if we had then used that, instead of our n in the formula we got over there, we would have gotten 0 is equal to negative 8, 5, negative 4, dotted with our P naught P would still be the same. x minus 2, y, z minus 5, which I'll just, instead of going through that whole process again, I'll just tell you what we would come out with. We would have gotten negative 8x plus 5y minus 4z is equal to negative 36. And that would have been the plane we would have gotten instead of positive 8x minus 5y plus 4z equals positive 36. So here's a question for you all. What's the relationship between the two planes given by these two different equations? Sarah? Anti-parallel? So what does it mean for two planes to be parallel or anti-parallel?
Is that just a line thing?
That's typically a vector thing, although we are going to talk about parallel planes on the next page. Jackson?
Are they identical?
Yeah. It turns out that if we had used W cross V instead of V cross W, the final equation we would have gotten would have looked different. But in fact, it's the exact same set of points. With the reason being, any XYZ that satisfies this top equation is automatically going to also satisfy the bottom one, and vice versa. If negative 8x plus 5y minus 4z does happen to give you negative 36, then you can just multiply both sides by negative 1, and you would get the exact same equation. And vice versa. If a point xyz satisfies this bottom equation, it would also have to satisfy the top equation. If we were to sort of look at a graph, turn this back on for a second. If we were to sort of look at graphically what's going on when we talk about that, here is kind of the VW, what happened to, oh, one's hiding underneath, oh no, here it is. So if V and W are these purple and green vectors, N is the vector sticking out, that 8, negative 5, 3 that we found, that's orthogonal to both of them. If we had wanted to, though, for a normal vector, we could have done negative 8, positive 5, negative 3. Still sticking out of the point. Somebody remind me what the point was. 205. Thanks. I'll make this one purple. And basically what it comes down to is if we had taken the normal, the negative of our normal vector, it would have given us the exact same plane. The plane containing these two vectors with this normal vector sticking out, this normal vector being perpendicular to both of them, is going to be the same as the plane where this is our normal vector, where the purple vector is the negative of the red vector. 8, negative 8, 5, negative 4 versus 8, negative 5, positive 4. It comes out to the same thing, and so whether you do V cross W or W cross V, in the end, might give you a different looking answer, but mathematically, it's the exact same set of points in the exact same way. Another thing, by the way, we could have done, if we had taken any non-zero scalar multiple of our normal vector, so get rid of this one. If instead of this normal vector, if we had taken half of it and done, say, 8 halves, negative 5 halves, 3 halves, still would have worked as our normal vector, just would have been a different length. But when you're talking about a normal vector to your plane, it doesn't matter how long your normal vector is, it just matters what direction is your normal vector pointing. So if you wanted to replace your normal vector with a scalar multiple thereof, again, it'll change how the equation for the plane looks, but it'll still be the exact same set of points in the end. Okay, that's it for today. When we come back on Friday, we're going to finish off Standard 4, talk about relationships between points and lines. You all have a good one. Talk to you on Friday.
Dr. Gersel.
Mhm.
Could I schedule a retake for tomorrow?
What
I'll
time?
do- It's just 1 o'clock for it at the start of your.
1 o'clock should be fine.
Okay.
If you don't mind, send me an email to remind me,
Will
and
do.
I'll make sure I have one waiting for you.
And it's for the dot product. So
Standard 2? Sounds good. Got a couple of retests ready for that.